All right, so let's start out with a few acknowledgments. This says work from NERSC, from Oak Ridge, and I wanted to include some special thanks to Zahar and Roman from Intel. They have been extremely helpful in answering our questions and helping to address our suggestions and work out any other issues that we've had with Intel Advisor. So let's start out with a brief introduction. So when we think about performance models and performance tools, why are we using them? Well, we want to identify any of the performance bottlenecks that we actually see in applications. We want to motivate some of the software optimizations to try to address those bottlenecks. But perhaps most importantly, we want to actually determine when we're done optimizing. That is, the performance model itself provides us with a goalpost that says, this is where you're done. This is, at this point, you're not going to get any kind of better performance from your code by doing continual software optimization. Moreover, we can actually assess our application's performance relative to the actual machine capabilities rather than simply saying we're 10% faster than we used to be. We can actually say we're within 90% of the machine's peak. Once we actually get there, we can actually use the roofline and that level of performance to actually motivate any algorithmic changes. That is, once we're at using the full capabilities of the machine, the only way we're going to get better performance on our application is to make fundamental algorithmic changes. One of the other areas we use performance models is in a co-design effort. That is, we want to actually predict performance on future machines or future architectures. So we can actually use the performance models to set realistic expectations for future procurement. That is, we have a future proposed machine, we can actually get some estimate of what the performance will be of various applications on that machine. Similarly, we can actually use it to address what the actual bottlenecks are on current machines to hope that future architectures address those bottlenecks in hardware. So when we think about performance models and simulators, historically, many of those performance models and simulators have tracked latencies to predict performance. That is, they try to count cycles. We can see this in cache simulators very clearly. But the last 2 decades saw a number of latency hiding techniques put forward by vendors. We have out-of-order execution. We have where hardware tries to discover parallelism at runtime to hide latency, whether this is memory latency or instruction latency. We have hardware, including hardware stream prefetchers, so that when detecting a certain miss pattern, the hardware can speculatively load data to try to hide the associated cache miss latency. And we have massive thread parallelism, where we can simply quickly switch between threads in order to always have some useful work to actually execute and thus satisfy the latency bandwidth product of the machine. And ultimately, effectively, these latency hiding techniques has resulted in a shift from a latency-limited computing regime to a throughput computing limited regime. That is, instead of being limited by latencies by nanoseconds here and there, we are limited by the underlying rate of which we can move data and perform computation. So the Roofline model is a throughput-oriented performance model. It's going to track rates, not time. It is augmented with Little's Law. Basically, the concurrency is the latency bandwidth product. And it is going to be independent of instruction set architecture for the most part and the underlying core architecture. So this allows it to be easily applied to CPUs, whether multi-core or mini-core, to GPUs, and even to Google's sensor processing units. Fundamentally, we have 3 main components in Roofline-based performance modeling. We have machine characterization. This is going to set some realistic performance potential of the underlying system. We have monitoring. That is, we want to actually characterize an application's execution. And then at another aspect, we have application models. That is, for the ideal architecture or the ideal compiler, how well can our kernel actually perform? And so that basically sets an upper bound to say, no matter what we do for optimization, no matter how well we can improve the architecture, here is the ultimate performance bound that we can get for our application. So let's start out with a simplified version of the roofline. In this case, it's a DRAM roofline. Now, ideally, one might hope that we can always attain peak flaws, but in reality, we have finite locality. That is, we have finite reuse of data. So I reference a array element in memory. I can perform so many flops on that, but that amount of reuse of that one array element provides a bound on performance. So we can plot that bound using arithmetic intensity as the x-axis. So arithmetic intensity is the ratio of flops to bytes presented to DRAM. Our performance bound, we can thus say, is not just simply peak flops, but also includes the actual bandwidth of the underlying machine. So depending on where we are in terms of arithmetic intensity, we can actually decide whether we're going to be compute bound or memory bound ultimately. That is, kernels with arithmetic intensity less than the machine balance are typically or ultimately memory bound, while those that are more compute intensive than the machine balance are ultimately compute bound. Now we can go through and think about a few examples of how we actually apply this. In practice, the typical machine balance, whether it's going to be a KNL or a multi-core processor or a GPU, is somewhere around 5 to 10 flops per byte. That's kind of a fundamental aspect of current process technologies, which basically says you're going to need to do 40 to 80 floating point operations per double to actually exploit the underlying compute capability of one of these processors. And ultimately, because this is an artifact of technology and money, it's unlikely to improve in the future. So let's consider stream triad. In this case, we're just going to do a simple vector-vector operation. Assuming n is sufficiently large that it doesn't fit in cache, we're going to do 2 flops per iteration, and we're going to transfer 24 bytes per iteration. That is, we read x, we read y, and we write z. This gives us an arithmetic intensity of about 0.166 flops per byte, which puts us heavily on the memory-bound regime. Now, let's think about another example where we actually increase arithmetic intensity. So in this case, we have a very simple canonical 7-point constant coefficient stencil in 3 dimensions. We're going to do 3 flops per iteration, and for each of those iterations, we're going to do 8 memory references. This includes 7 reads, a store, and ideally, the cache can filter all but one of those reads or writes per point. That is, with sufficient cache capacity, we can eliminate all but the cache compulsory misses. As a result, we have an arithmetic intensity of about 0.43 flops per byte, which, although is still memory bound, the Roofline model allows us to show that we will get higher performance, a higher flop rate for that underlying code. Now, we can extend the Roofline model to actually include multiple levels of the cache hierarchy. So any real processor is going to have many levels of memory. We can start with registers. We have L1, L2, L3, however many levels of cache. We can have a MC DRAM or HBM on the package. This is something like the KNL memory or the GPU's device memory. We then have DDR main memory, and in the case of some newer systems, we may actually have NVRAM in the memory space. So we can actually measure a bandwidth for each of those levels of the memory hierarchy and actually define an AI for each kernel, for each level of the memory hierarchy. So in this case, we may see that our given kernel has 2 arithmetic intensities associated with it. It has an AI, a flop to DDR arithmetic intensity, and it has a flop to MC DRAM arithmetic intensity. And we can see, based on the performance models and the relative bandwidth of the underlying architecture, that the DDR bandwidth in this case and the DDR arithmetic intensity is the ultimate bottleneck to performance. Now, we could imagine a different kernel, in which case we have much higher DDR arithmetic intensity. That is, we can imagine we fit the problem in MC DRAM and thus get substantial reuse, and as a result, the amount of data that we actually have to move to DDR is dramatically diminished. In this case, we can actually improve DDR arithmetic intensity, and now, as a result, MC DRAM is our ultimate bottleneck to performance. Now, this basically says that we need to know the arithmetic intensity and the relative bandwidth for each level of cache in order to actually bound the ultimate performance potential for any of our applications or underlying kernels. Now, we can similarly augment the Roofline model with data instruction or thread level parallelism. That is, we have nominally assumed that we can always attain peak flops if we have infinite locality, but the reality is that's not necessarily true. So a canonical example is that current architectures include a fuse multiply add instruction. That is, with one instruction, you can do a multiply add operation. Now, the question happens, what happens if your code just does adds and it doesn't do any multiplies? Well, basically that eliminates half of your performance potential. We can, by the same extension, think about what happens if we don't exploit vectorization. That is, on a machine like K&L, if you're in single precision, you might be able to do if you're in double precision, doing FMAs, you might be able to do 16 floating point operations per instruction. If we don't generate vector code but generate scalar code, we lose a potential factor of 8 or even 16 from our potential performance. There's also unrolling, that is, a floating point unit, like memory, has a certain latency associated with it, and we need sufficient parallelism to cover that latency. We also need, we have parallelism in hardware, so we need multiple threads, OpenMP threads, for example, CUDA threads, GPU, to actually provide sufficient parallelism across our compute resources. So we can, in the Roofline model, add additional what are called ceilings to our performance potential, which further bound the actual potential performance. So a kernel which might have been memory limited in the ideal regime may actually fall to being compute limited without vectorization. So at this point, I think I'm going to take a quick break and ask if there are any kind of questions to this point on Roofline.
Yes, actually. So there is one slide where you have 0.166, and I think there's a question where that number comes from. There, yes.
Hopefully, if I did this right, this is 2 divided by 24.
Right. Yes. And then in the slide 11.
So just to be clear, that was the 2 flops divided by the 24 bytes.
Right. Slide 11 now. Are these the same kernels? So then how do you get different AI for same kernel, for the same kernels for different memories?
So it can be the same kernel. So we can imagine a case where we have a kernel which has a active working set which might fit in MCDRAM but has a total footprint which may actually not fit in MCDRAM. So imagine the case where we have a working set which might be in total 30 gigabytes. That means that as we process that data, we may not be able to fully contain it within the MCDRAM. But within that kernel, we have an additional level of locality of, say, 8 gigabytes. So we can churn, perhaps in this particular contrived example, on that 8 gigabytes 20 or 30 times before we have to move to the next 8 gigabytes in our 32 gigabyte total problem size. So this gives us several tiers of locality where we can actually get locality in MCDRAM, but actually still have a problem size that actually fits in DDR.
Another question related to this, but the flop per byte doesn't change, does it?
Well, you will have 2 flops per byte. So you will have a flop per byte associated with MCDRAM, and you will have a flop per byte associated with DDR. So in both cases, the bytes, the denominator is the number of bytes being moved to that level of memory. So there's a certain number of bytes that have to be moved from DDR. There's a certain number of bytes that have to be moved from MCDRAM. The underlying kernel will do the same number of flops, so the numerator remains the same, but the denominator can change.
So another question here, Sam. Must the Roofline model be run utilizing all cores on a node, or can it be used on one core?
No. So you can certainly use it on one core. If in the case you want to actually test what is the Amdahl effect of this machine, you could theoretically collect the Roofline data for a single thread on a 60-core K&L and actually determine how much lower your associated MCDRAM and DDR bandwidths actually are. And that's a very useful set of numbers when actually deciding when running hybrid code, how much of a penalty there is for not accelerating certain, not threading certain loops.
What's DLP in slide 12?
DLP? DLP is data level parallelism. So it's essentially vectorization, or SIMD. And TLP is thread level parallelism.
I think that's about it, so just resume.
So at this point, let's switch and show how we actually use or collect roofline data using the Empirical Roofline Toolkit, using VTune, and using SDE. So in our basic roofline modeling, there are two main things that we actually have to start with. There is the machine characterization. This is the underlying system. Basically, it's questioning how does the system respond to a lack of FMA, DLP, TLP, whatever, and how does the system respond to reduced arithmetic intensity? That is, as I lose locality, how pronounced are the memory and cache bandwidth effects? That could be extended in the future to include how does it respond to NUMA, strided, random access patterns, whatever. But there's the corresponding aspect, which is how does, when I actually instrument my application, what are the properties of my application's execution? That is, when I sit down, what is the application's real arithmetic intensity as measured on the target machine? How does the AI actually vary with memory level? That is, the L1 AI or the MC-DRAM AI or the DDR AI. And similarly, how well does the app vectorize and whether or not it uses fuse multiply add? So the first question, how fast is my target machine? Well, there are a few challenges associated with this. It's not quite as simple a question as it might seem on the surface. We have a large number of systems. We have new ones that come out every year. Each of them is associated with a huge amount of documentation that one might need to assimilate in order to actually predict what the actual performance is. And unfortunately, the actual real performance numbers are often less than the kind of marketing numbers that are actually advertised for machines. This is actually further complicated by the fact that compilers can actually give up on big loops. That is, imagine I've reordered my loop nest, I've restructured my code to maximize locality, and the result is a very large, ugly inner kernel in my loop nest. Some compilers can actually give up on that and thus see degraded performance. So what do we do? Well, so our approach at LBL was to create a benchmark, the Empirical Roofline Toolkit, to actually characterize CPU and GPU accelerated systems. So in the most basic sense, it will measure the peak flop rates of those target machines. It will measure the bandwidth of each level of memory hierarchy, and it's written in a MPI plus OpenMP/CUDA version so that you can run on multiple sockets without incurring NUMA effects, or you could run on multiple GPUs on a single node in order to get the full potential of a multi-GPU node architecture. So we can actually run this on KNL. We see a automatically generated roofline figure that tells us what the bandwidths are at each level of the memory hierarchy, as well as the peak flop rate that can actually be attained. And we can actually also run it on Summit Dev with 4 GPUs. And we can see the relative performance differences of these two node architectures in the absence of any kind of theoretical performance number. This is the actual empirical performance that one can attain on these two machines. So on the second half of the question, which is application and instrumentation, this can actually be an even more challenging problem. And this is challenged from several different aspects. First of all, flop counters on CPU or GPU architectures can be broken, they can be missing, they can be disabled, like in the case of Haswell. And similarly, simply counting loads and stores, that is the number of bytes presented to the memory hierarchy as opposed to being filtered by the memory hierarchy is somewhat misleading because it doesn't really capture any of the reuse. Similarly, counting simply the number of L1 misses or the L2 misses is not a good proxy for data movement because it doesn't account for the fact that there is a autonomous hardware prefetcher there pulling in data before you actually miss. We have found that the DRAM counters are accurate, but the downside is they are privileged and thus nominally inaccessible to user mode. Similarly, if you want to actually make certain counters accessible, you may need certain OS or kernel changes, and those need to be approved by the vendor, for example, Cray, and then approved by the actual center, for example, NERSC, before they can actually be used by end users. So what do we do? So NERSC and CRD, NERSC is the production computing facility at LBL, CRD is the computational research division at LBL, collaborated on trying to figure out a methodology for actually characterizing applications running on NERSC production systems. That is, we want to characterize a production system, we don't want to characterize just performance on a standalone system. So to that end, we use Intel SDE. This is a binary instrumentation tool to create software plot counters. That way you don't have to worry if the plot counter is actually broken in hardware, or if it's poorly documented, or if it just gives you erroneous data. In theory, one could use bifull as well. We also used the Intel VTune performance tool, which was approved by NERSC and Cray, and is actually enabled on the NERSC production machines to be able to actually access the uncore counters. So the two of those gives us accurate plot numbers, and it gives us accurate DRAM data movement on Haswell and KNL based machines. And there is an associated web page here for those interested in seeing all the details of actually how one uses these tools to actually measure and instrument applications running on NERSC machines. So the NESAP project, this is NERSC's KNL application readiness project, used Roofline to actually drive their optimization and analysis on KNL. That is, they wanted to actually bound any performance expectations using the ERT relative to Haswell machines. We wanted to quantify DDR and MC DRAM data movement to actually understand whether or not KNL incurs more data movement than a traditional Haswell with a large shared last level cache, and actually understand the importance of vectorization. So we quantified some of those results in a few papers. They are linked on my website for those interested in reading the details of those. So when we actually sit down and run those, in this case, we're showing 3 of the NESAP codes: MFDN, which is nuclear many-body configuration interaction; EMGeo, which I believe is a Stencil code; and Pixar, which is a particle and cell code used for accelerator modeling. We can plot the roofline for both a 2-processor Haswell node. This is kind of a Corey phase 1 or Trinity phase 1 type architectures, or a KNL node architecture, kind of the Corey phase 2 type architecture. And then plot performance as a function of different application parameters or optimizations for each of those different machines. So for example, we see that in general, the KNL does have higher peak bandwidth, but we observe that the actual arithmetic intensities can be lower. And as a result, performance may not be as good. That is, you have higher bandwidth, but lower arithmetic intensity. Those can be a wash against each other. Moreover, the importance of vectorization can be actually very profound on KNL and lead to substantial speed-ups relative to original or scalar codes. Now, we can use VTune and SDE to collect this kind of application data, but ultimately we're having to compose several tools together. That is, we get a little bit of information out of SDE, we get some uncore data movement out of VTune, we have to throw those together into a graphing tool and hope that everything comes out and is easily visualized. But unfortunately, that's a pretty high burden to place on application developers or even highly motivated users. That is, we're forcing them to learn and run multiple tools. We're forcing them to manually instrument every routine in their application, or at least the routines of interest, and we're forcing them to manually parse, compose, graph the output. And moreover, this still lacks any kind of integration with a compiler, debugger, disassembly. So if you want to actually understand why your code is slow, then you still need to look at the compiler disassembly and run it through a debugger. So ultimately, NERSC and CRD wanted a more integrated solution. So at this point, I'm going to take a quick break and see if anybody had questions on the VTune SDE / ERT methodology.
Well, the only question I see here is, let's see, okay, so there's one here. On slide 19, what cache model or models were used for the byte denominator for AI?
Just to be clear, it's this slide 19?
Slide 19. That's what they are.
I may have inserted.
Oh, 18, sorry. It's just correct.
Okay.
420.
I think I inserted one extra slide from whatever the slides got sent out. If it is this slide that's being referenced, the flop to byte ratio is the flop to MC DRAM ratio for each of these machines. it flops to MC DRAM for KNL, and it flops to DDR for Haswell, because Haswells don't have MC DRAM.
There was one earlier here. What does the green line MC DRAM have for a Y offset for AI equal to 0?
So I think this was in the previous part.
So there is no, you can never actually have in the Roofline figure, you can actually, so Roofline nominally plots a log-log scale, and as a result, you never actually see the 0 intercepts. You could have an AI of 0 by having no flops in your inner kernel, but just have bytes. But then you really shouldn't be using a flop to byte ratio. But when plotting, because it's on a log-log scale, you'll never actually see a 0-0 intercept.
The last one here, let's see here. What are software AI counters?
So in hardware, theoretically, every time you do a multiply or a multiply add, in addition to the logic that goes into actually performing the arithmetic, there's another piece of logic which actually just simply counts how many times you've done that instruction or how many times you've done that operation. Now, because those can be broken and because they are not a high priority for vendors, software counters is an alternative method for actually counting the number of operations. So one can imagine taking either at the compiler level or through binary instrumentation, source code, and then every time you have a multiply in your source code, you have a separate counter, a separate variable that simply counts how many times you've done a multiply or how many times you've done an add. So in software, you are simply counting concurrently with the actual execution of your application, the number of floating point operations.
And there is an observation here that on KNL, there is no flop hardware counters. So how did you get those flop counts?
So SDE is the binary instrumentation tool. So we use the software flop counters provided by SDE.
Okay, so let's move on for the next session, please.
So at this point, I want to take a slight divergence, it's an important one, and discuss the difference between Roofline and what the literature calls a cache-aware Roofline. So there are two major Roofline formulations in the literature. There is the original, which is also called the DRAM, or it's also called the Hierarchical Roofline. This is in the original CACM paper, Communications to the ATM. It defines multiple bandwidth that we talked about earlier. It defines multiple bandwidth ceilings and multiple AIs for every kernel. The performance bound is going to be the minimum of the intercepts of each of these AIs with their corresponding bandwidths and the associated flop rate. Now, there's also a cache-aware Roofline, which appeared in computer architecture letters a few years ago. Now, in this case, it defines multiple bandwidth ceilings, but uses a single arithmetic intensity, and that arithmetic intensity is the flop to L1 byte ratio. So as one loses cache locality in the cache-aware version, that is, you have capacity misses or conflict misses, performance falls from one bandwidth ceiling to the next at a constant AI. So why does this matter? Well, some tools use the original Roofline, some users use the original Roofline, some use the cache-aware, and it's important to know the differences so that when it's presented to you or when a tool that you're using uses one or the other, you know how to interpret the data. Now, perhaps more importantly, and germane to this presentation, the Intel Advisor tool nominally uses the cache-aware Roofline model, but there is an alpha/experimental version that actually uses the DRAM Roofline that we're going to be evaluating. Now, generally, I think CRD and NERSC prefer the hierarchical Roofline as it provides greater insights into the behavior in the memory hierarchy. So let's go through a quick example comparing the two. So both Roofline and cache-aware capture cache effects. In Roofline, the AI is the flop to byte ratio for each level of the memory hierarchy after being filtered by all the lower levels of the cache hierarchy. Conversely, in the cache-aware version, the AI is the number of bytes is the number of bytes presented to the L1 cache. That is, it's basically an L1 arithmetic intensity. In the traditional roofline, you have multiple arithmetic intensities, while in cache-aware it's a single. And as a result, the AI in the traditional roofline is dependent on problem size. That is, as you scale up the problem size, you may incur capacity misses. Capacity misses increase the number of bytes moved to DRAM, which means your denominator, your AI denominator gets bigger and your AI overall gets smaller. Conversely, the cache-aware version is independent of problem size. So we can directly observe locality and cache effects in the traditional roofline model, but they are kind of indirectly observed in the cache-aware version. Now, perhaps the biggest issue is that the traditional roofline requires performance counters to actually measure AI. That is, we really need to know how much data is actually being moved to DRAM, which in NERSC-based machines has meant access to the uncore performance counters. Conversely, the cache-aware version requires only static analysis or binary instrumentation to measure AI, and thus it's much, much easier to implement and doesn't require any kind of special permissions or privilege levels to realize. So let's go through an example. So in this case, we're going to go back to our simple stream triad example. Once again, we're doing 2 flops and 24 bytes. We have no cache reuse, and as a result, we end up with the same DRAM AI as the L1 AI for problems that don't fit in cache. So let's think about how we plot these two. So if in the traditional roofline model we had a DRAM line and an L1 line, we can simply plot the associated AI. In this case, it's the same AI for DRAM and for L1, and show that the performance is actually ultimately bound by DRAM. Conversely, in the cache-aware version, once again, we have always just a single AI, and we can actually look at what our observed performance is and show that it is highly correlated with the DRAM bandwidth. So at this point, we can think about moving to a slightly more complicated kernel. This is our 7-point Stencil. We have 7 flops, 8 doubles that we move. In theory, at the L1 level, we have a AI of about 0.11, and this is assuming compilers don't do any kind of fancy register shuffling to reduce the number of loads. But in reality, we have some degree of cache reuse. That is, some of the references in our stencil are reused from one iteration to the next. They are reused within the cache hierarchy, and as a result, the DRAM AI tends to be larger than the L1 AI. Basically, DRAM moves, we move less data to DRAM than we move to and from the L1, but of course bandwidths are different. So if we were to plot this in the traditional version, the traditional roofline will have 2 arithmetic intensities, one for L1 and one for DRAM. We can plot the intercepts for the 2, and in this case, we might say that the actual performance is going to be the minimum of the 2, and it is bound to the DRAM bandwidth. Conversely, for the cache-aware version, we have a single AI based on the flop-to-byte ratio presented to the L1. We have an observed performance that is somewhere between the L1 and the DRAM line. That is, in reality, if we just look horizontally across here, we're getting the same performance number in terms of flops, but in the cache-aware roofline, we see a observed performance somewhere between L1 and DRAM bandwidths. Now, we can actually infer that that says we've got some level of cache locality, but not full locality in the L1. Now, if we go from a small problem to a larger problem, that is, we move from, say, a 256 cubed grid to a 512 cubed grid, what happens? Well, going from small to large in the traditional roofline model means that we get the same L1 AI, but lower DRAM AI. Essentially, we're incurring capacity misses. Conversely, in the cache-aware version, the AI remains the same, but the performance decreases, indicating we have lower reuse within the cache hierarchy, and thus we're, on average, seeing memory bandwidth associated more with DRAM bandwidth for every memory reference. So I know those two concepts can be, between the traditional roofline and the cache-aware roofline, can be a little complicated, so I want to take a quick break here, see if there are any questions.
I don't see any questions here. Oh, no, there is one here. Can you reiterate how the 0.44 AI was obtained?
So the 0.44 is more a estimate in this case. I don't remember if it came from the empirical data, based on if you were to actually run this on a machine, how well does the cache hierarchy filter out all of the memory references that we present to it. So in this case, it basically is getting something like, well, in the asymptotic limit where we have no capacity misses, if we go back to the Stencil code, ideally we would have just filter out all but the reference to the right of new and the leading element of old, which means 16 bytes and 7 flops. So I think you can take 7 and divide by 16 and probably come pretty close to 0.44.
So going back to slide 20, the conclusion was that all the apps were memory bound?
Ultimately, they are bound by memory bandwidth. That is, for the arithmetic intensities that these NESAP codes have, they are ultimately bound by memory bandwidth. That doesn't say that the actual implementation at a given instant is completely bound by memory bandwidth. We observe on something like Pixar that it is still difficult to actually hit the memory bandwidth limit, and particularly difficult in the original implementation without any kind of tiling or vectorization. So there is performance potential on these codes, but ultimately there's only so much we can gain through on-node optimization, because we can only make it as fast as DRAM without a fundamental algorithmic change.
Another question here, how does the spatial locality affect AI?
So if we are streaming through memory, then ideally we have high spatial locality. And by spatial locality, we can say, whether or not when we access elements at address I in memory, whether it's highly likely we will access elements at I+1, I+2, I+3. So for streaming codes, we have high spatial locality, and thus we use all of the data that we stream through. But we can imagine in the case where we have a array of structures data layout where we may only access every 5th element or every 8th element. In that case, we have lost arithmetic intensity, and this becomes we have lost arithmetic intensity because the number of bytes presented to DRAM is the number of cache lines, essentially, that we're having to access from DRAM. So if we're accessing every 8 bytes of memory as presented to the memory hierarchy, the memory hierarchy will still move every byte from memory, because it will move data in full cache line granularities. And thus the arithmetic intensity can suffer greatly.
Thank you. Let's move on then.
So at this point, we're going to switch to a demo of Intel Advisor. This is going to start out with just an introduction and general usage, and huge caveat that the DRAM Roofline part of Advisor and the OSX Advisor GUI are preview features and may not actually be included in the mainline product. Intel is providing these features in order to collect user feedback. So Intel Advisor it's a very nice integrated performance analysis tool. It provides performance information, including timings, flop, trip counts. It provides tips for vectorization. It gives you memory footprint analysis, and perhaps most relevant at all to this talk, it nominally uses the cache-aware Roofline model. Now, all of this information from individual kernels, memory footprints, vectorization tips are all connected back to the original source code, so that in a single environment, you get all of the information you want. So to that end, CRD and NERSC began a very effective collaboration with Intel. We wanted to ensure that Advisor actually runs on Cori in user mode. We wanted to actually also push for a hierarchical roofline. That is, we wanted to see the effects of the cache hierarchy on arithmetic intensity. And we also wanted to make it functional, scalable in the case where we have many MPI processes across either a single node or across multiple nodes. And then finally, we wanted to validate the results on various NESAP, SIDAC, and ECP codes. I've included a few useful links to provide background on Advisor. There's also another demo of Advisor on YouTube, and there is a NERSC webpage on how to actually use Advisor on the NERSC systems. So I'm going to switch at this point and have Tomas give the demo. So can you
okay, so let's switch to my screen really quickly. There we go. So I'm just going to show the same slide. So here are instructions on how to run Intel Advisor on NERSC to instrument an application. So compiling is easy. There is not much extra needed. You only need to include the -G for debug flags, and then you either start an interactive session with the salloc command or submit to the batch queue by writing a sbatch script. You don't need anything different if you're using the product 2017 Advisor version that we recommend for users. There are extra, you need to add, basically give extra permissions to the Anchor counters for the DRAM Roofline that I'm going to show briefly at the end. But that, like Sam said previously, is still an experimental version. To collect the data, there is an Advisor module that you need to load that links you to the Advisor binaries. And after that, we recommend collecting data using the command line interface to Advisor, which has this complicated name advixi-cl. To collect all the information for Roofline, you need two collections, and this is because the first collection, which is on the first line here, -collect survey, is a sampling-based collection that is used to get the timings for the loops in the application and various other survey data like vectorizations. And this is very fast, so it should run in roughly the same time it takes to run the application normally. The second part is the trip counts collection that actually collects the flops and the bytes, and this is an instruction counting collection, so it has a fairly high overhead. You can expect something like 5 times your regular runtime. But once these two are collected, and I want to point out here that you have to specify the same project directory to Advisors where it creates a database, and then the trip counts collection just adds more data to it. You can launch the Advisor GUI. So this you can do on a login node. The collections should be done on a compute node. And again, you just load Advisor and then launch the GUI with this advixi GUI command. So I've run these collections for the Stencil code that Sam was talking about, and now I'm going to switch over to the GUI, and in this first part of the demo, walk through the GUI quickly, show what's in there and how to access the Roofline. So the first thing you see is when you open the GUI is a welcome screen, and here you can open your result. I've already done that, so I'll just go to show my result, and that should take you to a summary screen that looks like this. So this gives you some general information on your application. Things like you can see that the total number of flops has been counted, the total AI is here. you see that we run this using 16 CPU threads. So this was run on a single socket Haswell node, of a single socket of a 2-socket Haswell node. You see metrics for vectorization efficiency, and then you see your top time-consuming loops highlighted. The real stuff is under this Survey and Roofline tab, and once you go there, it will break up all this information by loops in your code. So here in this example, we have 5 main loops that are using roughly the same amount of time. You can see that here that you have the flops for each loop, the AIs for each loop, and then if you move further, you see information on how well the loops have been vectorized, what are the vector lengths, what are the trip counts, what are the instructions that have been issued, data types, and so on. And in the bottom part here, it actually links this information directly to your source code. So I can click on one of these loops, and it will point me to the line in the code where this loop starts, and give even some information by source line, such as time and what instructions have been issued. There are multiple tabs here at the bottom that contain useful information. The top-down gives a top-down structure of where the time is being spent in the code. So in this example, we have these 5 loops called bench stencil version 0 to 4 that are each using approximately 1/5 of the time. You have this code analytics tab. I find this very useful. So it gives you a summary on the instruction mix that your application has used. So we can see that about 1/3 of our instructions are accessing memory. Then we have compute instructions, mixed instructions, which are basically compute and read or write, and then something else that could not be categorized. So this gives you a nice quick overview of what the code is actually doing. You can view the assembly if that's your thing, and this also highlights blocks of pins blocks of assembly code to the source code of your application. So the point of this talk is the Roofline. So there is a Roofline tab here on the left, and you can click on that, and it shows you the Roofline, and it shows every loop of your application on the Roofline chart separately, and it colors and cites the points with regard to the time that's spent in them. So in here, all of the loops spend about the same amount of time. So I want to repeat that this is the cache-aware Roofline. So you see here that all of our loops have the arithmetic intensity of 0.12, which is, I think Sam mentioned 0.11 was what they expected. So we're pretty close. And here you can move over them with the mouse. You see the flops you're getting, the AI that's been measured, and still you can navigate back to the source code to see what the individual loops are doing. I should mention that the roofs here are based on measurements. So when you launch Advisor, it runs a small benchmark to measure these bandwidth and flop loops on the system you're running, and usually these numbers are pretty accurate.
So Advisor does that for you?
Advisor does that for you automatically, so you don't need to give any commands for that. There's an option. So this is a threaded code. So we're running this on 1/2 of the node. these roofs obviously correspond to the whole node, so we should expect to reach about half of the peak performance. There's an option if your code is not ready to go to roofs for a single-threaded application, which can be useful. And I think they're working on increasing the flexibility here to show you roofs for running single socket, for example, that we would ultimately like here. Okay, so this was a quick overview of the GUI. So there are screenshots on the slides of the things I just went through. Are there any questions at this point?
I think there was, let's see if someone is going to ask a question about this. There is one that I think remained here. Is there a tool to calculate DRAM AI or L1, L2 AI for a complex application code? Instead of not only small kernels.
So in principle, Advisor, you can run Advisor on a complex application code. The limitations are kind of that the runtime should not be too long. So in the order of minutes is probably still okay. And if you have a hybrid code that uses MPI and OpenMP, it will analyze every MPI rank separately, and that can create a lot of overhead. So we recommend just collecting Advisor data on a single rank and looking at that. So the question was about DRAM and L1, L2. So at the moment, Advisor only does L1. We are working with Intel to produce a version for DRAM, and it's pretty far along. So I will show you, if I have time in the final part, an example of this stencil code with the DRAM Advisor. And I think L2 is on our shopping list, but I think Intel has only so many resources to dedicate to this other time, so they will work on it in the future, I hope.
Okay, so two related questions here. Is the Roofline plot you showed for the whole application, or the loop, or just the loop you have highlighted?
So the whole application in this case only has these 5 loops that are plotted here on this roofline. I think I've heard Intel mention a feature that allows you to sort of collapse all these loops into a single point on the roofline, but it's not in the release version yet. But that's also something that might be coming in future versions.
Okay, so now, can we annotate a specific region of code to be profiled instead of a whole application, similar to vTune macros?
That's a good question. I don't remember exactly if Advisor supports the same start-stop markers that vTune does. Okay, I have to check that.
We are keeping these questions here and make sure that they are going to be answered in the Google Docs, and we'll make the answers. We'll run the questions through the speakers again to see if to make sure all the questions are answered in detail. So another question here is: can this tool be used to Python or Cython?
Well, I'm not an expert. I think the answer is yes, but all the features might not be there. So they focus mostly on C and Fortran. I know that I think they have a version for Python, but I haven't used it, so I can't really say how complete it is.
Just to add, the DRAM version requires OpenMP to highlight basic blocks.
So we have more questions here. Is there still a piece of
so there's still a short piece of about 5 minutes that I should I go through that now?
Yeah.
Okay. So I want to talk about a little bit about this stencil code again. So we have prepared the 5 loops you saw in the previous example. So we prepared 5 versions of the same 7-point stencil loop that highlight different optimizations that you might make in your sort of optimization workflow, and we're gonna just go through them quickly to show how that changes where the application sits on the 2 roofline models. So we use a 512 cube domain on a single NUMA node, so a single Haswell socket, and this is basically just to eliminate any possible NUMA effects that might show up. And the 5 versions. So in the first version is a sort of a naive implementation where you are striding, or you are not telling the compiler how long your strides are in any of the 3 dimensions in memory, and to make sure that the compiler doesn't try to vectorize this, it also has a no vector pragma in it. So this is like a scalar version of the loop. Then the first optimization is to enable vectorization by removing this pragma and also specifying that the innermost loop of the stencil is unit strided, so that one can be vectorized. Then the second optimization is to add some cache blocking, so to reduce cache misses by blocking the outer loop, so that you can work on a set that fits in cache at the time. And then after that, additional optimizations are to improve vectorization by providing aligned pointers and strides, and then finally to force vectorization with the SIMD pragma and use non-temporal stores to bypass cache. And so I'm gonna go back to this that I was showing previously. So the cache-aware roofline. You can see that all these optimizations have the same AI, because this is the AI to L1. So no matter how you change your memory access, the AI will always look the same, and you're just gaining performance by doing these optimizations. So you can see that the bottom point here is version 0. The top point here is version 4, which you can see in the name on the tooltip, and we go up to somewhere between DRAM bandwidth and L3 bandwidth. So we get some cache use that takes us above DRAM, but not ideal cache reuse that would push us up to L1 or L2. So now I'm going to switch over to the experimental DRAM Roofline version, and look at the same code, and now I have again 5 points on the roofline here, but now the AI is changing when we apply the optimizations. So in the first optimization from version 0 to 1, which is just to enable vectorization, we gain about a factor 2 in flops. So we go from about 5.5 flops to 10. This is on a Haswell with AVX2, and like I said, we're only using half of the node. We're only using one of the 2 sockets, so we can only expect to reach half of the memory DRAM bandwidth of the node, which is pretty much what we've done here. And then by adding cache blocking, so you're now reducing the number of data you have to move from DRAM. So that increases your AI, and the second version has gone up from an AI of about 0.17. So I should point out that even the basic stencil has some cache reuse. So instead of 0.11, we have an AI of 0.17, but with the cache blocking, we get an AI of 0.28, and then going up to the last optimization, we get to 0.41, which is close to the 44 that Sam mentioned in his slides. Okay, so since time is running out, I think we'll stop here and wrap up and take some questions.
I just wanted to add, back on the previous slide, just to invite people to, maybe this one, invite people to come to the SC17 Roofline/Advisor tutorial on Sunday, November 12th. It will be a half-day tutorial, and it is certainly a multi and mini-core focus.
With that, Ashley,